Okay, first question, what is K? K is the number of clusters. So, in K means you always start with the number of clusters. Okay, you have to input how many clusters you want to start with. Okay, and as in the case of agglomerative clustering, that is something that we decided at the end. Okay, or you don't have to specify that number to start with, but in partitioning or in K means you have to specify the number of clusters. Okay, and therefore how would you start with? Okay, how will you start? How do you know what should be the number of clusters? Okay, that's a valid question. Okay, so you can keep speculating. K should be 3, 4, 5, 6, 7, 8, 9, 10, but that is not fair, right? There has to be some method, okay, to calculate or to estimate the number of clusters. So, we will see that. Okay, but assume there are K clusters. Start with K clusters with centers chosen arbitrarily. Okay, so there is a random seed. Okay, we call it random seeds to start with. Random seeds are random points in the space. Okay, Euclidean space or multi-dimensional space, depending on the number of attributes. You start with those random points and then you follow a method to assign each object to those seeds and iteratively improve the assignment, so that clusters become so low in errors, or within cluster distances are minimized. Okay. So, you follow an iterative process for that. So, I will explain the K-means algorithm graphically in the subsequent slides. Okay. You can write it in textual form, which is followed, which can be followed, which is there in your textbook. I am trying to explain it graphically. Okay. So, K-means algorithm, this is a different textbook. Okay. So, you may benefit from this, okay, because it gives you easier visualization of the K-means algorithm. Okay. So, as I said, assuming that there are only two variables, okay, and it is a two-dimensional space, and you have n number of objects, you can count the number of objects here. Okay. And the starting point is random, 3 random seeds. Okay. You are saying K equals 3. Okay. That is my assumption. I want 3 clusters. Okay. For some reason I assume that, okay, my assumption. And which are my assumed starting points? There is one point here. What is this color? Magenta, and this is blue or green. This is a green, red, okay, M, let me call it M, okay, M, G, R. Okay, these are random MGR, okay, random seeds, okay, in the Euclidean space. I start there. So, you can also assume that if two people do a K-means, okay, their solutions can be different because your starting point is different. Okay. So, it is based on these starting points, you start to sort of continuously iterate going for minimization of total errors and finally arrive at some solution. Okay. So, what is done is, of course, select this random seeds and go to the next slide. Here you see the next step in the algorithm. The next step in the algorithm is to assign each object to one seed. Okay. Keep in mind, if I give you a data set in a spreadsheet, okay, you must be able to do this assignment by calculating centroids and continuously doing the assignment. Okay, it's an important exercise that you should familiarize yourself with. Okay, I am explaining that here. So, you have the random seeds. So, and what is done is you fixed those seeds here and here, and then what you do, you calculate the distance of each object to each of the 3 random seeds. So, for example, there is one object here, I calculate the distance of this object to this, I calculate the distance of this object to this seed, I also calculate the distance of this. Okay. Now, where does this guy belong? This guy belongs to that seed with the shortest distance. Okay. That is where I belong, that is where the distance is the shortest, or that is where the similarity is the highest. Okay. And therefore, visually you can see that this guy should belong to this point. Okay. This is the shortest distance, and similarly you assign each object to that seed where the distance is the shortest. Okay. That is the first iteration, first level of assignment. Okay. Each object gets assigned to one of the seeds to which it is closest. Okay. And then you see, you notice one interesting point here, that is, there is an object here, this guy. Okay. Initially, because the seeds are placed here, when you look at the distances, distance to this, and distance to this. Okay. We actually calculate, it appears that this is a green object. Okay, because this distance is the shortest. Okay. So, this fellow got assigned to this group, that is the green group, and not the magenta group. Okay. Although visually you will see that this guy belong here. Now, the next step is, these assignments are done in the first step. Okay. Second, you calculate the centroids of each group. Now, there are 3 clusters formed, calculate the centroids. The centroids is not the same as the seeds. Okay. Centroids got shifted here, okay, or now the centroids are here. Okay. These were the initial random points, but when the assignment happened, groups got formed. Now, you find the centroids of the groups. Okay. That is the central point of the cluster. Okay. That is the next step, and now also there is a scope for reassignment now, correct. Now, calculate the distance of each object to the 3 centroids. Okay. Calculate the distance of each object to the 3 centroids. Okay. Now, for example, take this guy who was assigned to the green group. Okay. Calculate the distance of the distance to the centroids. Which is the shortest distance? Yeah, this fellow actually is closest to the magenta group, and therefore, there is a scope for reassignment. Okay. So, in the second iteration, you reassign each object based on distance to centroids, okay, distance to centroids, and therefore, he changes group, okay, from one party to the another, okay, from ADMK to DMK, or you know, MGR to something else. Okay, just for fun. Okay, so the based on distance, okay, you actually change or reassign each object to another group. Okay, now it does not end here. At this stage, now again, since the reassignment happened, this is a very simple case, okay, where you say that one person changed party or group or cluster. Now, what happens? The centroids change again, because reassignment happened, the centroids again change. So, you recalculate the centroid. Okay. When you recompute the centroid, again there is a chance that some objects would change the clusters, because the distances again change. Okay. So, you see the iteration going on. So, in each iteration you compute the total, E is the total error or total within cluster distance. Okay. Okay. The function, the purpose is to minimize this, okay, minimize total within cluster distance, and you expect that the error should be, if this is the error should be falling with each iteration. Okay, that is what you expect. And the minimization function is the total within cluster distance. What is Ci? Okay, suppose there are k clusters, for each cluster you calculate the total within cluster distance, which is the distance of each object to the centroid. Distance of each object to the centroid, you sum it up for each cluster and you sum it for all the clusters, you get the total within cluster distance. Okay. So, the idea is through each of the iterations, the solution should be converging, or it should be, the error should be falling till it reaches an acceptable value, okay, called the minimum error acceptable. You know, in an algorithm, you can set a minimum value for error. You can also set a minimum value for tolerance. Tolerance is the incremental change in error that happens between iterations. Okay. So, these are values or hyper parameters you can tune within an algorithm, within a clustering algorithm.
So, why did we do distance square?
Squared distance. Okay. Square has certain mathematical properties for minimization, that is for minimization, that is one explanation, and that is the only explanation I can give. Squared error is used. Otherwise, you can use a sum of absolute errors, okay. But for a minimization algorithm, you typically use the squared error. So, for this particular cluster, the P minus Ci would be the distance of this cluster to distance, this one all squared, okay. That would be the sum of squares for one cluster k equals 1. For k equals 2, you go here, find the total error. For k equals 3, you go here, find the total error with respect to the centroid. Sum that up, and that is the total error. No, you are breaking down, you are actually going to, so you are looking at whether the features, each feature would be, you know, what data type, okay. That challenge would be there. So, in terms of, you have to establish some way of calculating or transforming the data type into one standardized format, and then do this, okay. And this can work only if it is continuous valued. For interval, ordinal and continuous valued data, this is a simple formula, okay. Otherwise, it becomes a challenge, okay. Okay, that is the detailed level of computation, but essentially at the level I am explaining, it calculates the total error with respect to total squared error with respect to centroid. Okay. Okay, so we have seen this method goes on until the final solution converges. Okay. Now, there is a challenge here, that is with respect to determining the number of clusters. We talked about it, right? What is the value of k? Okay, k, as I said, there is a practical consideration. You ask the manager or your project sponsor, okay, how many number of clusters would be acceptable, okay. That is a practical consideration. Then there are heuristic techniques, okay. One heuristic is how many number of clusters? If n is the number of objects or number of records, square root of n by 2 is one suggested number of clusters, okay. And there should be a square root of 2n data points in each cluster, that is a minimum cluster size, okay. This is heuristics, one recommendation, okay. This may conflict with the practical consideration, okay. So, you know, these are sort of suggestions. Another widely used method for determining the value of k is the elbow method, okay. Elbow method is very intuitive and very useful, because the researcher can choose the number of clusters as a range also. You can also, you know, try out a 3 or a 4 or a 5 and see how good the cluster solution is and decide. But where to choose that range from, okay, is something that can be determined using a elbow method, okay. In the elbow method, the x-axis is the number of clusters, okay, and the y-axis is nothing but the error. The error can be the total within cluster distance, okay. Now, what is done here is you employ one algorithm, one clustering algorithm. It could be the k-means algorithm, okay. You run k-means with 2 clusters, 3 clusters, 4 clusters, 5 clusters, 6 clusters and so on, okay. And plot this graph, okay, the total within cluster distance versus number of clusters, okay. And then you find that after some stage, okay, the error actually doesn't change much, okay, it's like the elbow, okay. There is a steep fall here, then it becomes almost same, it doesn't improve much, okay. So therefore, the elbow is the point that one should fix as the optimum number of clusters. So that way, some graphs may give an exact elbow like this one, okay, 4, okay, but sometimes you don't find a clear elbow, okay, sometimes the hand may be little stretched and so on. So therefore, you can try, if I am working on this problem, I will not just go by this recommendation of 4 alone, I would try this one, I would try a 5 also or a 6 also and see how interpretable the cluster is, okay. A cluster should be interpretable and useful, okay, it is for a purpose, and I would choose that solution. I will combine an elbow method with a practical consideration, okay, and that is where sort of you can fix the number of clusters, okay, you can decide the number of clusters, okay. Now, since partitioning techniques are widely used, there are different choices of clustering techniques within the partitioning method. One is of course the k-means, which we discussed already, and there is something called time complexity or cost of computation that is involved in an algorithm, which is minimization algorithm, and time complexity is given by sample size, number of clusters and number of iterations, okay, that determine the time complexity. And one challenge with the k-means, since it is actually for centroid it is averaging, okay, the centroid is a average of the feature values and therefore solution is sensitive to outliers. A centroid can lie at one corner of the cluster if there are actually outliers, okay. So therefore, you have the k-medoid, okay, I think I wrongly printed it as m-medoid, it is k-medoid, okay. Medoid uses not the mode, please see the difference between medoid and k-modes. K-medoid is different from k-mode. In k-medoid, you find the center value, not center value, the most central object, okay. Suppose there are say q number of objects within a cluster, okay, you find out that object which is most centrally located, instead of just going for the centroid which is the average value, okay. The mean can be influenced by the outliers, instead of that use the most central object as the reference point to calculate errors, okay, and then use that, that is the k-medoid technique, okay. And this solution you expect to be better than the k-means if you are aware of too many outliers, okay. That is second technique. And k-mode works for data when the data are categorical, okay. You can use the mode instead of the mean, okay. So that is the k-modes technique, okay. So k-means, k-medoids and k-modes are variants of the partitioning technique, okay, depending on the data type, that is k-means and k-mode, and depending on the reference point for calculating errors. So k-medoid is an improvement on k-means, okay. I will so cluster quality, okay. We will the last 10 minutes we will try to have problem, but we will try today or we will do it in the next session, okay. It's better to understand concepts well and then go to a problem, okay. So cluster quality, at the end, what is the quality of the cluster that you obtain, okay. Of course, you can look at the errors and then speculate about the cluster is good or not good, but it is better to have a ratio always, right, to comment on something instead of going by some absolute value of error. Okay. So, there are certain ratios that are available, known as, one is known as the Silhouette coefficient, other is known as the F, okay, Pseudo-F. Okay. Pseudo-F and Silhouette coefficients are widely used to report quality of clusters that were formed. Okay. Now, the extrinsic methods which is given in your textbook refers to those methods where the cluster classes or the labels are already given. Okay. Like that is more close to a decision tree kind of exercise where the class labels are known. Okay. In most cases when you use clustering, there is no label. Okay. The clusters get formed based on closest distances, you have to label them. Okay. In our exercise you will see, you are the person, you as researcher or analyst would finally give a name to a cluster. Okay. This is a Punjabi cluster, for example, or this is DMK, AIDMK, or this is BJP or Congress or whatever party, you know, you name them based on their characteristics or their affinity or affiliation. Okay. There are attributes that we capture, group and then name them. Okay. So, take it all in a lighter sense. Okay. Don't take it to heart. Okay. That's all, you know, just how we form social groups. Okay. That is also based on certain social attributes. Okay. All right. Now, so what is the Silhouette distance? It is clearly explained, taken just from Han and Camper. So, suppose AO is the average distance between O, which is an object O, and all other objects in the cluster to which O belongs. Okay. And BO is the minimum average distance from O to all clusters to which O does not belong. Okay. The value of Silhouette distance is given by BO minus AO divided by maximum of AO or BO. But intuitively, what is this formula trying to tell you? Okay. There are 3 clusters and there are objects within clusters. Okay. O is here. Okay. The fellow O is here. Okay. O belongs here. Okay. So, what is AO? Is the average distance between O and all other objects in the cluster to which O belongs. Okay. O's distance to his friends, his or her friends. Okay. All his friends are in that group. Okay. What is the distance of me to my friends? Okay. That is AO. Okay. But what is BO? What is the distance of me to my rivals? Okay. If it is political party. Okay. So, there are people that belong to other parties. Okay. What is my distance to other objects? Okay. So, O's distance to all other objects. Okay. That is what BO is. Okay. So, that is what you desire is O should be close, okay, to his or her friends. Okay. But O should be far from the enemies, okay, or rivals, okay, in a competition or in a, you know, in that scenario. Or clustering has to be taken that way, in the sense the cluster should be close, cluster objects should be close within, but they should be very different. They should discriminate from other clusters. Okay. So, it is a measure of how well a cluster discriminates versus how well a cluster is homogeneous. Okay. So, homogeneity versus heterogeneity. So, BO is a measure of heterogeneity across clusters, right, the distance of O from other. AO is a measure of homogeneity within that group. Okay. And therefore, what do you want? What should be maximum? AO should be maximum or BO should be maximum? There you failed the test. Okay. You want BO, the error should be maximum when I consider my distance from others. Okay. So, BO should be maximum. Okay. And BO should be, when BO is maximum, AO should be minimum. Okay. At that points, the ratio will become 1. Okay. But in a scenario where BO is not maximum, AO is maximum, then BO is small. Okay. BO is small. Therefore, denominator becomes very high and BO is small. Therefore, this will have a negative value, right, and therefore, it will tend to -1. That is what the range is going to be. Silhouette distance will have a range of this kind. Okay. So, it gives you a sense of homogeneity and heterogeneity across and homogeneity within. Okay. Pseudo-F is another ratio. Okay. Look at that ratio, it is very intuitive. Between cluster sum of squares divided by within cluster sum of squares. Okay. And like degrees of freedom, it is also trying to consider number of clusters. Okay. So, simply look at that ratio between cluster sum of squares divided by within cluster sum of squares. Okay. It is actually again similar to what Silhouette distance is trying to do. Between cluster distance should be high, okay, within cluster distance should be low, and therefore, you want an F value which should be high. Okay. A higher F value is desirable, correct. The denominator should be low and the numerator should be high, okay, just like the F ratio in your statistical test. Okay. And this gets sort of moderated by the C minus 1 divided n minus C divided by C minus 1 ratio. Okay. For example, when the number of clusters is equal to the number of objects, what happens to this ratio? What n minus C becomes? C is equal to n, okay. So, it becomes 0 or F value will become 0, right. So, therefore, it does, it's for number of clusters, it moderates the value, okay. So, it should be C should be much lower than n, okay. Only then this ratio would give a good value, okay, or reasonable value, okay. So, that is the measure of F or pseudo F, okay, in assessing cluster quality, okay. Two measures, Silhouette distance and pseudo F to measure the cluster quality at the end, okay. And if you are doing a clustering exercise, you should report this cluster quality measures also, okay. Okay, at the end, since you are students of business, when you do a cluster analysis, it is not for satisfying yourself with how you have done a nice data analysis, nice values of F and Silhouette distance and so on, close your project. No, your project actually starts here in analytics, okay. You did this exercise to present your solution to as project sponsorer, okay. Project sponsorer has sponsored your project for solving some business problem, okay. So, you have to take it to the sponsorer and satisfy yourself with the measures of quality, but present it for practical application, okay. So, segmentation using clustering, okay, in such exercises, cluster profiling, okay, profiling a cluster is a very important exercise, okay. You describe the cluster, okay. If you formed 5 clusters, what are the clusters known for, okay. This is an example where Claritas Prism, which is a professional agency which does segmentation in the United States and maybe other countries too, using zip codes and lifestyle attributes, they form geographical clusters, okay. See how they do this job and how they sell their product. Their clustering product is sold as well profiled clusters, okay, geographical clusters. You see what they do, movers and shakers, this is class label or cluster label, okay. Movers and shakers, looking at the characteristic of a cluster, they gave a name, okay. This cluster can be named as movers and shakers, okay. In decision trees, you know that the cluster labels or the class labels were given, okay, like bias or non-bias. Here there is no label, you look at the cluster characteristics, well, this cluster consists of people who have these characteristics high, okay. How do they describe the cluster? You see, it is for application. Movers and shakers is a cluster, is home to America's up and coming business class. Therefore, the business class attribute is having high value here, whichever attribute they used for that. Wealthy, they have used income as a attribute, okay. And this cluster has average income which is high, average income which is high, okay. You have to look at the each cluster and compare based on some measure of average, okay. And comparatively, this is a wealthy group, okay. they are suburban, okay. Dual income, all are attributes, okay. Dual income couples, okay. I think this is becoming common in our country also, right. Dual income couples, okay. So, they have used that as an attribute, okay. Highly educated, so education is one attribute, okay? And it is high because average value is high, okay. Typically between ages, so age bracket is another attribute, but you see the how they position it for a user, okay, or a decision maker, okay. When you cluster, got good solution, go for a presentation, take something of this kind, okay. Your backend analysis is with you, you have control on that, but in presentation, look at the cluster profiles, okay, and describe them in a way they can appreciate it for application. Well, is this cluster useful for me, or is this segment useful for me? Depends what product or service I have, right? And they would make that recommendation as consultants, okay. Another group or another cluster which they have profiled, and name is given by them, okay. Prism Claritas, that's a clustering exercise for analytics, okay. Clustering for classroom work, you can do up till your F value and Still-Houghton distance, but if you have to make a presentation or make it useful for analytics, then you also have to look at the profile. So, in our example which I am going to use in the class, I will try to profile the clusters, okay, using graph, so that you get to understand what each cluster is, and then subsequently you can name the clusters and then describe them using language, okay.